Okay. Yeah. This situation is better than I expected. Okay. We had earthquake last night, right? I'm very sleepy now because of earthquake. I just couldn't sleep very well. I hope you guys sleep well last night, but at least I didn't. Yeah. So that's why I got my cup of coffee. Okay. So hope you don't fall asleep like in the class. Okay. So today we are going to talk about one of the most famous problems in computational geometry. Okay, we're going to talk about the problem, how to solve it, as well as the variant, okay, of this problem. Okay, we actually use this problem to motivate the computational geometry at the beginning of this class. It's called post office problem. Okay, I think we have a couple of post office on campus, and how a student decide which post office or which phone. Okay, if I remember correctly, we use the public phone. Okay, as an example on campus as an example to motivate this problem. Like if we have a couple of public phones on campus, how do a student, how do a person decide which where to go to make a phone call? Okay, so based on such consideration, we can divide the campus into a number of areas, right? So at that time, okay, I talk about this problem, but the more formal name is called post office problem. So we are, we want to establish a number of post offices, okay, and to service people, of course, and the setting of this problem is just like the public phone example I used at the beginning of this class. Okay. Okay. The assumption for this problem, okay, are as follows. Okay. The price of a particular good or service, okay, in this case, okay, we consider it's the service provided by the post office, okay, will be the same at every site. Okay, when I say site, okay, in this chapter I'm referring to a post office, or in the beginning of the semester, the public phone. Okay, we call such a location that provides service as a site. Okay, and the cost of acquiring the good or service is equal to the price plus the cost of transportation to a site. So basically, like the cost depends on how far away, how far the distance you have down through, okay, to acquire the service. Okay, so because of this consideration, so a customer, okay, will prefer, obviously, will prefer to get the service, because the service is the same for every site anyway, right? So the customer will prefer to get the service from the nearest site, okay, nearest site, okay. And the cost of transportation to a site equal to the Euclidean distance to the site times a fixed price per unit distance. That's why, okay, we care about distance, okay. And when it comes to distance, of course, like that's one important element, one of the important elements in computational geometry, okay. So our customers, okay, try to minimize the cost of acquiring the good or service. Okay, so that is why, okay, we assume the customers will use the nearest site to get the service, and he or she will go straight to that site. We do not assume there are obstacles to block your direction. Okay? So, as you can see, okay, these assumptions are more abstract, okay, in the sense that it could be used for post office, it could be used for public phone, it could be used for a number of applications, obvious, okay? And this problem, okay, is well known as Voronoi assignment model. Okay, this model where every point is assigned to a nearest site. Okay, we call this model Voronoi assignment model. Okay, and under this model, okay, your plane, okay, two-dimensional plane, will be divided into a number of subdivisions. Okay. And we call this subdivision induced by this model as the Voronoi diagram, okay, that we obtain from a given set of sites, of course. Okay. As I said, there are, you know, even though like post office or public phone problem seems to be more artificial, okay? It's not like it's a real problem, but they are based applications of this Voronoi diagram concept, okay? For example, physics, astronomy, robotics, okay? So you can see that if this concept is applied to across many fields, okay? And other geometry structures. Actually, the other geometry structures, when we discuss them, I mean, we may also base the discussion on the top of a Voronoi diagram. Okay, for example, okay, the next chapter that we are going to cover is the online triangulation. Okay, we talked about triangulation earlier, right? We talked about triangulation earlier, but at that time, the triangulation is not confined by certain requirements. But dynamic triangulation is a particular triangulation that is like you know, we need to triangulate a given set of points, but it's based on certain criteria. Okay, so it's the consideration is much more complicated than the one that we discussed earlier. Okay, but the dynamic triangulation in the next chapter, the discussion is also based on the Voronoi diagram. So you can see that, okay, this Voronoi diagram concept is actually a very important one. Okay. If you ask me, okay, what problems are the most representative like problems in computational geometry? Okay, I will give you three. Okay, I actually will give you three. Okay, Voronoi diagram will be one of them. Okay, what are those three? Okay, I mean, you also have learned one of them earlier already. Okay, the convex hull. We talked about convex hull at the beginning of the class, right? Okay, but that convex hull is a very simple one. Okay, we assume only two dimensions, right? later on, okay, at the later part of this class, I hope to cover like a more general convex hull, which is like a higher dimension convex hull. Okay, so that's of course one of them, and then the second one is vulnerable diagram. The third one actually is the de-Lorentz triangulation. And you can see de-Lorentz triangulation is related to vulnerable diagram. So obviously, I mean, this vulnerable diagram concept is very important. Okay? So, okay. So given a set of sides, okay, well, the side it's just a point, right? So it will be the same as given a set of points. Okay, we represent those sides or points as P1, P2 up to Pn. Okay, we have n distinct points. Okay, in the plane. Okay, you can call them points or sides. Okay, in this chapter, I mean they can be used exchangeably. Okay, so we define the Borno diagram induced from this set of sides as a subdivision of the plane into n cells. Okay, so each side will be associated with a cell. Okay, the property of each cell is that a point Q will lie in a cell corresponding to a side. Okay, Pi. Let's say that side. That cell is for the side Pi. Okay, if and only the distance between Q and Pi is the smallest. Is the smallest. Okay, compared to the distance from Q to any other side. Okay, so one of the example will be something like this figure. Okay, you can see we have the sides are represented by black dots, right? And these black dots, okay, because of these black dots, we can divide the 2D plane into this many cells, and each cell basically has such a property. Okay, the points in a cell, for example, the point in this cell, they are closest to this side. Okay, compared with any other side, in this given cell. Okay, so for the notation, okay, we represent distance like this. Okay, it shouldn't be difficult to understand, right? And this distance computation is just a Euclidean distance. Okay, Euclidean distance. And also, we can denote, the Borno diagram induced by the set of side P by VORP. Okay, this is just a notation. So we can call this Borno diagram. Okay, if we call this set of sides as P, then the VORP will be this Borno diagram. Okay, and the cell for VOP, that corresponds to a particular side Pi, we call that VPI. Okay, this is just for ease of discussion. Okay, so you need to understand these notations so that we can have a better, easier way to represent certain concept. Okay. So at the beginning, the problem, of course, I mean, in this chapter, the most important problem in this chapter is how do we, efficiently calculate this Borno diagram. Okay, and just by looking at this figure, you you know, I think you can tell. I mean, this Bono diagram has vast applications, right? I mean, for example, even like in biology, okay, when you look at the cells, okay, the cell structure will look like this, right? Okay. So there are so many applications for that. I mean, this dot, I mean, looks like they look like the nucleus for the biological cell. Okay, so this is like a very common. If you notice, you should be able to find such a figure, something similar to this one, like across different research discipline. Okay, so how do we compute this? Okay, so let's start from the simplest consideration. Okay, say we only have two sides. If you have only one side, you don't need to do any division, right? Because, well, the nearest side, of course, is that single side, right? So the whole two-dimensional plane would be one single cell for that particular side, right? Okay, so, well, obviously this is not any very challenging, right? So now let's take into account two sides. If you have two sides, what would be the situation? If you want to, construct, well, you can say it's Bono diagram. It would be, if you for given two sides, okay, you can just like say like these two sides are P1, P2. Okay, so you can just draw a bisector which is perpendicular to the line P1, P2. Okay, that will be your Voronoi diagram. And by the way, I told you like at the beginning of this class that I don't think I can finish every chapter in one lecture, right? Remember, this chapter will be one of them. Okay, so I expect to spend about 1.5 weeks on this chapter. Okay. Nevertheless, I will assign. Okay. Nevertheless, I will assign the third homework assignment today. Okay. I mean, like, of course, that was cover this chapter, right? But the due date will be 2 weeks from now anyway. So next week, you still have like plenty of time to finish to work on chapter homework 3. Okay. Give me 1 sec. I don't know why they don't design they design this marker, wrapper so difficult to remove. 为什么怎么设计这么难打开？因为刀子那种。对呀，上面就是报纸。对啊，其实找一家公司做这个。Anyway, okay. So if we without loss of generality, okay, let's assume those two sides are something like this. Okay, because orientation distance doesn't matter, right? I mean, you can just rotate your two-dimensional surface and then scale their distance a little bit, right? So it doesn't matter. So you just if you want to use P1, P2 to break this surface such that all the point in one cell, okay, will be closer to, for example, P1, and the point in another cell will be closer to P2. One simple, geometry property that tells you is that you are looking for the bisector of this P1, P2 line segment. Okay, at the point after the bisector, they have equal distance to P1 and P2, right? Right? You should have this concept from junior high, right? Junior high school. When you understand what a bisector is, right? 就是分支平分线 Okay, so basically once you have this, okay, this part belongs to P2, and this part belongs to P1, right? Okay, and we normally represent this, okay, each of these as a half plane. Okay, half plane because it's not a full plane, right? It's bounded by a line, so we normally call such a plane as such a space as a half plane. Okay, and let's assume, okay, the bisector, okay, that the half plane formed by the bisector of P1, P2, okay, as H, okay, P1, P2, and H, P2, P1, okay? So this one, okay, whichever, half plane that has a point closer to one side, say for example this one, because the points are here are closer to P1, so the P1 will be written ahead of P2. Similar logic, okay? The points here are closer to P2 than P1, right? So the bisector of this bisector is denoted as this one. Yeah, this one denotes this one. Again, this is just a notation, okay? It helps us to have a discussion for the following material. Okay? So far so good, right? Okay. So, okay, once you understand this bisector thing and half plane concept, it should not be surprised. It should not be a surprise to you that, okay, a Borel cell for a given site Pi, a Borel cell for a given site Pi would be the intersection of all the half planes, okay, intersections of all the half planes, Pi, Pj, where of course Pi is a fixed point, fixed site, but the Pj range from 1 to of course not, the same, I and J are different. Okay, with the constraint I and J are different. So this should be very clear to you, right? Because the volume, the point in this VPI are closer to PI than any other sites, right? Okay, so if a point is closer to PI, then, for example, to the other side, PJ, then it should fall inside the half, inside half PI, PJ, right? Right? It should be inside the half plane of PI, PJ. And, you know, the same thing, okay, can be said for all the other sides of PJ. Okay, so then it's the intersection of all these half planes. I mean, you get this volume scale. So this is interesting observation. Okay, obviously we could you know, compute the volume diagram based on this observation. Okay, basically just like you know, compute the intersection, and then sorry, we compute the half planes, and then try to, you know, for each side we try to calculate its scale by using this idea, right? And but you know, this is a little bit more costly, okay, because we are talking about computing intersection of well, if we have n sides, then we are talking about computing the intersection of n minus one subdivision, right? We need to basically like overlay n minus one subdivision to get the intersection, right? And this is just for one cell, right? We need to do this for every cell. I mean, even though you say, oh, if you do this for every cell, I mean, we should be able to do some optimization, but you could imagine, okay, I mean, regardless, you have to overlay n minus one, or n, okay, you have to overlay n different like bisectors, and that's like not an easy job. Okay, you know, we talk about plane, you know, map overlay. Okay, and it's not, it's doable, but it's just like not a good way to calculate it. Okay, to compute it, because it's time consuming. Okay, to get the cell, okay, you need at least linear time, right? So obviously it's going to cost you like more than at least n squared. And easily could be n squared log n, something like that. Okay, so you don't want to do that. Okay, even though that's a possible approach. So what do we do? What do we do? We want to, you know, here we want to talk about like some idea that is like they can compute that volume diagram even faster, even faster. So let's continue like look into the property of the volume diagram for given set of sides P. Okay. So first, let's look at the vertices, the number of vertices, and number of edges for the volume diagram. Okay. So let P be a set of n-point sides in the plane. If all the sides are collinear, then your volume diagram will consist of n-1 parallel lines, something like this. So, I mean, if all the sides are collinear, I mean like they are located on one line. For example, I mean we have this P1, P2, right? And if you have a third point, say this is P3, and they happen to be on the same line, then you can imagine, okay, you need to calculate the bisector for every pair of them, right? For every pair of them, and but because they are collinear, they are on the same line, so the bisectors will be, I mean, all these three bisectors will be parallel, right? Will be parallel. And then, okay, you would find that, okay, it's going to, if I use this, say this is the center, the middle point for between P2 and P3, okay? And we draw another vertical line. So this, you will find that, okay, the Borel diagram will be these two parallel vertical lines, okay? Because all the points here are closer to P3. All the points here are closer to P1. And in between, they'll be closer to P2. Right? And you could easily, okay, you could easily extend this concept to n sides that are on the same line, right? So, okay, this is what I meant, okay? If all sides are collinear, then Borel diagram of this set of points will consist n minus 1 parallel, okay? Should be very easy to understand, okay? If it is not the case, if all the points are not collinear, you just need to have one point. Just need to have one point that is not on the same line. Okay? You don't need to, be very complicated. Just one point that is not on the same line. Then, okay, the Borel diagram will be connected. Okay? And its edges are either segments or half lines. Okay? So here we can see like one very special case, right? Like we have one, all the other sides are surrounding this side. Okay? Something like that. And the Borel diagram will look something like this. So you can see that, okay, yeah, the edges, okay, are, for example, these are the edges. So these are the edges that are, segments, okay? And we have other edges like this. They are, half lines, okay? So this observation, you may think, well, this is, of course, this is the case, I mean, but think about this. When the n sides are on the same line, the edges for the Borel diagram are straight lines, right? So it's different, right? It's different. Okay. So, okay. For n, okay, if your sides, number of sides is greater or equal to 3, okay, we know that the number of vertices in the Borel diagram of a set of n-point sides in the plane is at most 2n minus 5. And number of edges will be at most 3n minus 6. Okay. Why is that? Okay. You could we know like Euler formula give us this, right? For plane, you know, general like planar graph, okay? The number of vertices minus the number of edges plus number of faces will be 2. Okay, so this is what Euler formula gave us. Okay, but well, from the previous discussion, we do know one thing, is that okay, you could have some line segments as edges, which is not an issue. Okay, because like when we discuss planar graph, like line segments, okay, not an issue. Okay, but when we discuss, but how about half line? Half line, like this, the lines that go infinite, far away. What do we do? Here, okay, for the ease of discussion, we could assume, okay, these lines, when they go infinite, okay, they actually will reach, they will all reach a vertex called V at infinite, V infinite. Okay, you may ask, okay, how can this happen? Because, well, on two-dimensional plane, you feel like, well, if two half edge are, you know, going on different directions, shouldn't they be more far away from each other, right? But if we talk about polar coordinate, 极坐标 polar coordinate, like, or you can imagine, you try to put this thing on a globe. The coordinate system used on Earth. Okay, if all these are going infinite, it's just something like if you try to imagine this graph is on the North Pole, okay, 北极 North Pole, and all this infinite half line eventually will converge to at the 南极 South Pole, right? Okay, you can imagine it's you try to fit this thing on a two-dimensional, on the pole, on the surface of the pole. Okay. Then, okay, it will become a closed planar graph. Okay. Keep in mind that this equation, okay, will hold only if this is a planar graph. This is a planar graph. When I say a planar graph, I mean there's no like half lines, because half lines, you know, if a graph contains half lines, it's not considered as a planar graph. Okay, so that is why we try to introduce one more vertex at an infinite location and try to, you know, have all these half lines converge to that point. I mean, by doing so, this you know, your Born diagram will become, okay, conceptually will become a planar graph. Okay, so you can apply. Then you can apply this Euler formula. Okay. Okay, so now let's take a closer look at this Euler formula. Okay, so number of vertices. Okay, we know the number of vertices. Okay, will be, well, it will be. We don't know how many vertices. I mean, we have actually. I mean, keep in mind, we are not talking about sides. Okay, we are talking about, for example, this as vertices. Okay, we are not talking about the sides. Okay, so we don't know how many vertices we have. So we will denote that the number of vertices as NV. But we need to add one because that one represents this additional these infinite vertices. That is a vertex, obviously. Okay, so it's going to be NV plus 1 for NV. Okay, NV will be NV plus 1. NV is the number of vertices for your monoid diagram. Okay, and we don't know introducing this vertex doesn't add any more edges, right? So the NE will be NE, okay, will be the same. Number of edges will remain the same. As for number of faces, okay, we know each face, face is like a space that is surrounded by edges, right? So in this case, well, each side exactly will be one face, okay? And since we have each cell will be exactly one face, I'm sorry. Each cell will be exactly one face. Since each side has a cell, so the number of faces will be exactly 10. So from this one, this Euler formula will become something like this. So N is given, obvious. N is given, but we don't know NV and NE, right? So we have the first formula. Okay, we have two unknowns. We have one formula, and we need one additional formula. Okay, the second formula is very easy. Okay, we use this concept actually a little bit earlier. Okay, let's consider the total degree. Okay, each point, each vertex has certain degree, right? A certain degree. And if you try to add a degree from every vertex, that's the total degree. Okay, and if you still remember the handshake theorem that you learned from the discrete math, okay, then you should know that the total number of degree equals to 2 times the number of edges. Okay, because each edge contributes, 1 for each end, 1 degree for each end, right? So the total number of degree will be 2 times the total number of edges. Okay, so we consider total number of degree. Okay, on the left hand side is 2 times number of edges. Okay, this is the exact estimate. Exact estimate. We could have another way to estimate. What is that? Okay, let's consider for each vertex. Each vertex, well, if you have a vertex, that vertex, the degree must be greater or equal to 3, right? Right? Otherwise, how can you create a vertex? See here, okay? Each vertex, the degree will be at least 3, right? For this, okay, the degree of each vertex will be at least 3, right? Obviously, you could have more than 3, right? You could have more than 3, but the degree of each vertex is at least 3, right? So using 3 to estimate the degree for each vertex is a lower bound, right? Okay, it's a underestimate. It's an underestimate. So how many vertices do we have? Remember, we have NV, right? Plus an additional node we introduced. This additional node, obviously, its degree should be more than 3, right? should be more than 3 too. Well, let's still use 3, okay? So you can see NV plus 1 times 3. Okay, this is another way to estimate total number of degree, right? But, of course, this is an underestimate. The left-hand side is exact estimate. The right-hand side is underestimate. So, of course, exact estimate will be greater than or equal to this underestimate. Okay? So, with these two formulas, okay, you could, okay, derive this, okay, for n sides, okay, the number of number of vertices, okay, which is NV. NV is at most 2n minus 5, and number of edges for Born diagram, okay, is at most 3n minus 6. So these are very important because we know, okay, the number of edges and the number of vertices are linear, right? They are linear, which will help us to estimate, for example, like storage complexity, okay, complexity analysis at a later time. Okay? So that's, well, it's already 9:50. So let's take a 10-minute break. When we come back, we'll continue our discussion. Okay? Okay, there's a questionnaire that I need your help.带进去看，两个都一样的。你把 NB 跟 NB 这样子带进去，就只剩下 NB 跟 N 对不对？那就可以得到 NB 跟 N 关系。你把 N 那个。